welcome back to Chemicals Academy. So we discussed outer sphere mechanism in previous video, and in this video we will see about inner sphere mechanism. So in inner sphere mechanism, the oxidant and reductant. Oxidant is oxidizing agent and reductant is reducing agent. So these two complexes will be sharing their ligand, one of the ligand. So one of the ligand will be sharing between these two complexes. That's the main principle behind inner sphere mechanism. So in outer sphere mechanism, we have seen the oxidation and reduction, just transferring of electron from one to other. But in inner sphere mechanism, a bridging ligand is present. What is bridging ligand? A ligand which can share a pair of electrons. So a ligand which have an unshared pair can act as a bridging ligand. So the examples for bridging ligand is halides, OH minus, CO, Cn minus, NCS. So I have written here OH minus, CO, O2 minus, NH2 minus, N3 minus, Cn minus, halides, fluorine, bromine, chlorine, iodide. So these are bridging ligands which have unshared pair of electrons. So in inner sphere mechanism, the oxidant and reductant, oxidizing agent and reducing agent share a ligand, that is a bridging ligand, and form a bridged complex. And the bridging ligand is the ligand having unshared pair. And this is very important. The two complexes are there. So let's say M1 and M2. So the M1 and M2 are labile or inert in outer sphere mechanism. So for the factors favoring outer sphere mechanism, where what it should be high spin or low spin, or inert complexes are more preferred for outer sphere mechanism. It should be same. But in inner sphere mechanism, one complex will be labile and another will be inert. So one complex will be labile and another complex will be inert. So usually the reductant will be labile and the oxidant will be inert one. So in inner sphere mechanism, main factor is the one complex is labile and another one is inert. And I have said how to identify the inert and labile complexes by looking on the T2G configuration. So the greater unshared pair electrons increase in bridging nature. So we can write the order of the bridging nature of the bridging ligands by looking on the unshared pair of electrons. Greater the unshared pair of electrons, greater will be the bridging nature. So another point is the fluorine, chlorine, bromine, the halide order. So greater the size of the halide, greater will be the bridging nature. So which is greater in size? Iodine. So iodine will have greater bridging nature. So it will have greater bridging nature due to greater in size. Why this is depending upon the size. When size increases, the polarizing nature increases. So for sharing the electron pair, the ligand should have dipole moment. So when polarizing nature increases, what the dipole moment also increases. So for increasing the dipole moment or for increasing the sharing tendency of the electrons, it will have higher size, higher dipole moment, higher polarizing nature, higher bridging nature. So the best bridging ligand is iodine among the halide. So OH minus, CO, O2 minus, NH2 minus, N3 minus, Cn minus, NCS, etc. are bridging ligands. So inner sphere mechanism is sharing of ligand or transfer of bridging ligand from one complex to other one. So we can see two examples. In first case, in this case, the transfer of bridging ligand is taking place, but in second case, there is no transfer of bridging ligand. So I already said there are cases where the bridging ligand is not transferred. So that's also inner sphere mechanism. So in first complex, CuNH3 5 times Cl2 plus. So we can write the configuration of cobalt 3 plus. So this is cobalt 3 plus and D6 is the configuration. And this is a low spin complex, cobalt 3 plus. So low spin, so T2G Eg configurations, T2G6 and Eg0. No electron in Eg orbital, so this will be a inert complex, inert one. Now coming to chromium complex, Cr2 plus. So chromium 2 plus is configuration D4. and this is a high spin complex. Water is a weak ligand. So D4, T2G3 and Eg1. So one electron in Eg orbital. So this will be a Love complex. Now we can write the mechanism, the reaction between these two coordination sphere. So the bridging ligand is chlorine. So the chlorine will be sharing with the chromium complex and the cobalt complex, coordination sphere. In outer sphere mechanism, the coordination sphere is not changed, but in inner sphere mechanism, the coordination sphere is affected. So the intermediate will be NH3 5 times, then cobalt metal, then chlorine is shared with these two sphere, then chromium, then one water molecule is eliminated from this sphere, then CrH2O 5 times. So the total charge will be 2 plus 2, 4. 4 plus. And one water molecule is eliminated. Now what happened? The chlorine, this bond is break down and this chlorine is transferred to this coordination sphere from the cobalt sphere to chromium sphere. Now the product will be cobalt NH3 5 times. So for satisfying the coordination number, the water molecule will attach to this sphere. So H2O. So the charge will be 2 plus. And now this is transferring to here. So Cr H2O 5 times Cl2 plus. Cl2 plus. So the chlorine is transferred to chromium. Now when we do hydrolysis, what happens? This ammonia is replaced by water molecule. So we will get CO H2O 6 times 2 plus Cr H2O 5 times Cl2 plus. And this complex is labile and this one is inert. In this example, the chlorine, the bridging ligand is transferring from one complex to another one, from cobalt sphere to chromium sphere. So now in second example, there is no transfer of bridging ligand. So here FeCN6 3 minus, COCN6 3 minus. So the bridging ligand will be cyanide ligand, Cn minus, or we can write NC, NC minus. So the mechanism will be FeCN 5 times, then cyanide ligand, then cobalt Cn 5 times, then a Cn minus. So here what happened? When you eliminate this bond, the cyanide will be going to the cobalt, breaking FeCN bond. So FeCN bond is break. But here FeCN bond is more stable than cobalt cyanide bond. So for due to that stability, this cyanide iron bond is not break down and the cyanide ligand is not transferred to cobalt sphere. So that's why here the bridging ligand is not transferred. So there are some cases where the bridging ligand is not transferred from one complex to other complex, but they are also inner sphere mechanism. So in first example we have seen the bridging ligand transfer, and in second example there is no transfer of bridging ligand due to the stability of the bridging ligand and the metal complex. Let's see another example of inner sphere mechanism. IrCl6 3 minus and CrH2O6 2 plus. Here also chlorine is the bridging ligand. So what is the role of bridging ligand? It will transfer electrons to other sphere. So the bridging ligand is not transferred. Cl5 IrCl CrH2O5. IrCl6 3 minus is again formed, but here CrH2O6 3 plus. So the transfer of electron is possible through bridging ligand without transferring the bridging ligand to other complex. So these are examples for inner sphere mechanism.